I don't know if this problem has a name, but I'm going to solve it anyway. So let me describe the situation, and I already did a video. My previous video, which I'll link down below, goes over the solution to the differential equation for the equation of motion for this problem. But now I want to completely model it. So here's the situation. I have this table, a frictionless table, and you can get these online. You just Google frictionless physics table, and there's a mass on the table with a hole in the middle, and then there's a string connecting the mass on the table to a mass hanging down below, and I want to model the motion of this thing with Python. Okay, so I'm going to give you a brief review of what we saw on the last episode. So we're going to use the Lagrangian mechanics because this is a system that's constrained, and when you have constrained systems, Lagrangian works really well. So it starts off with the principle of least action. So action is S, and so suppose I have some function L, which we call the Lagrangian. Here it is. It's the kinetic energy minus potential energy, and we use T for kinetic energy. It's because I think it's from the French. It's a French origin word. I don't know. We use T. Okay. So we can get a function for kinetic and potential energy, and this must satisfy the equation that we integrate from time t1 to t2, and we get some action. The real path is the Lagrangian that minimizes this action, and that's why this is called the principle of least action. So how do you find a function that minimizes an integral? Well, that's where the Euler-Lagrange equation comes in. So this says that if you have the function L, it will be a stationary state, so either a maximum or a minimum, but it turns out it's a minimum, such that the partial of L with respect to one of the variables, q, and this is a coordinate, we could say, q is a coordinate, minus the time derivative of the partial of L with respect to the velocity, q dot, is equal to 0. Okay, so this is the Lagrangian there. I have an introduction to Lagrangian that's a lot more detailed. I'll post it down below. So here's our problem again. The first thing that we need to do is how many degrees of freedom and how many coordinates we're going to have. There's only 2 degrees of freedom. If I pick two things, I could say 2 numbers, and you know exactly the orientation of the system. And so the 2 things that I could pick are the distance of mass 1. Mass 1 is the mass on top of the table from the hole, and the angle from the starting point. With mass 2 is dependent on r. Okay, so I can still have another variable s, and I'm going to use that. I use that in my original solution, but it's constrained. It's not an actual variable because there's still just 2 degrees of freedom. So I'm going to use the generalized coordinates r and theta for this problem. And I'm not going to go over all the details because I did it in the previous video, and I even just copied here's a picture of my solution. The Lagrangian for this situation depends on r dot, which is how fast it's moving towards or away from the circle, r, the distance from the circle, theta dot, which is the angular velocity, and that's it. Okay, so that's the Lagrangian. The next thing I would do is take the partial of that. I have 2 variables, so I got to do the Euler-Lagrange equation twice. The first thing I'm going to do is take the partial of L with respect to theta, and you see it's 0. There's no theta in there. Then I can take the partial of L with respect to theta dot, and I get mr squared theta dot. And that, since I take the derivative of that, it has to be 0 since the partial of L is a 0 with respect to theta is 0. Then that means this m1 r squared theta dot has to be a constant. And we pick that constant to be the lowercase l, not uppercase L, because I already used that for the Lagrangian. So you can't use that again. Now if I do the same thing for r, I have to take the partial of L with respect to r, and I get that. And then I take the partial of L with respect to r dot and take the derivative. Boom, I get these 2 equations. Okay, so again, I flew through that. Okay, I even skipped some steps in the last video I did, but it's better, it's more detailed. So that's where we are. We want to now model this solution because we have an expression for r double dot, and we have an expression for theta dot. So how do we actually make a visual representation of this whole thing? So here's my solution. This is the same thing on the previous page. So r double dot, and then I have an expression for theta dot. Now there is one condition that we want to consider. What if, and I go over this in the previous video too, what if I make the mass on the top move in a circular orbit, which I can do, right? In that case, I know the following must be true. The theta dot squared has to be equal to this. And we can choose, we can calculate the tension in the string and use centripetal acceleration to find that. This is going to be important in our solution because we can test this. I can put in theta dot as the square root of that thing and then see if I actually do get a circular orbit. So that's important. Okay, let's go on to a numerical calculation. So that's really what we're going to do. So the key to a numerical calculation is to break the problem into small steps of time. And so at the beginning of that time, we know the values of position, velocity, angular position, and then we can calculate the values at the end of the time step and then just keep redoing that over and over and over again. So we're going to make some assumptions during that small time step. This is the Euler method. Technically, it's the Euler-Kromer method, and there are more advanced methods. Okay, but this one I think works well enough, and we can check it. So we're going to use this because it's easiest for students to understand, and I make this for students mostly in the upper level undergraduate physics course. Okay, so here we have our R double dot equation. I've already shown this is the third time. Okay, so that's just from the Lagrangian. Once I know R double dot, I can define R double dot, and again, I missed this just to be clear. R double dot is a notation for the second derivative of R with respect to time. Okay, just to be clear. We use that. It's very common. And it looks cool too, right? Okay. So R double dot is the derivative of R dot with respect to time. If I take a short time interval, I can actually write that as the change in R dot divided by the change in time, assuming R double dot's constant, which it's not. But if delta t is small enough, I can assume that. And that's really part of the big nice thing here in the numerical calculation. I can rewrite delta R dot as R2 dot minus R1 dot. So here I'm using the notation R1 dot is the velocity at the beginning of the time interval. R2 dot is the velocity at the end of the time interval. If I multiply both sides of this equation by delta t, and then I add R1 dot to both sides, I get R2 dot equals R1 dot plus R double dot delta t. Now, technically that's R double dot at the beginning of the time interval because I just calculated it. Okay, but here you see something super powerful. I can calculate R double dot and then use that to find the new R dot. I can update R dot. So this is like your velocity update formula. And it's not true, but it's pretty good, especially the smaller delta t, the better this is. Now we can do the same thing for R dot. So R dot is defined as the derivative of R with respect to time. So I can write that as delta R divided by delta t. And then again, I can say delta R is R2 minus R1 divided by delta t. So using the same algebraic step, R2 is R1 plus R2 dot delta t. And now here I did put a number at the indice for R2 dot, right? I just calculated the new velocity. So I'm actually using the velocity at the end of the time interval rather than the beginning of the time interval. And that's part of the Euler-Kromer method. Okay, if you could change that around, you could change these orders up, but this is the way that works probably the best in the simplest steps. Okay, so now I've started with R double dot. I've updated R dot. I've updated R2. I've updated the position. What about theta? Well, theta, I know this is the expression of theta dot for my Lagrangian. And L is a constant that I can get from the initial conditions. So yes, theta dot does change, right? Because R changes, but I can calculate it. So I'm calculating theta dot. And theta double dot, 0. We already showed that. So again, I can say theta dot is the change in theta over the change in time, which is theta 2 minus theta 1 over delta t. So I get theta 2 equals theta 1 plus theta dot delta t. It's just like the R thing, except it's theta. And then finally, I can do this. I can update time. Okay, so I want to know the time at the end of the time step too, because I'm going to have a solution with time. So I can update time based on my time step 2. So there we go. So let's just review. So first is to calculate the R double dot. I get that from an equation from the Lagrangian. Next is to use that R double dot to update the velocity, the R velocity. Next, I update the R position based on that R velocity. Next, I go to the angular velocity, which I calculate based on the Lagrangian. Then I update the angular position. Then I update time. Okay, so this is our recipe for the numerical calculation. And I need to code that. And I could just code this and plot R versus theta or R versus time, and I could do a whole bunch of great stuff, and I probably will. But I also want to make a visual representation of that. And this is where we get into the artistic side of a numerical model. Yes, there is art. So here is what I want to make. And I'm going to show you how to make this here, and then I'm going to start with that already made. But I want to show you how it is. So this is a three-dimensional object with actually multiple objects in GlowScript VPython, which is a module for Python. I'm going to actually use trinket.io because you can do this all online. And I want to build this three-dimensional object. And in this case, I actually have a table, I have two masses, and I have a hole, and I have two strings, which it really should be one string, but it's two. Okay, so let's go through the different steps. Here's my table. I want to make this. How do I make this table? Well, there's really two important components to this object in Python. I need to know the center of the object, which is called the POS for position. And then I need to know the size of it. And the size is actually a vector. I need to know the size in the X, Y, and Z direction. This is the code to make that table. Okay, so I have G and I have the masses. That's just something I picked. I picked those masses. Actually, my students wanted these masses because they were trying to be funny. It doesn't really matter what they are. I'm going to leave it. I was doing this in class, and my students said, hey, let's use this 5.3. It's an inside joke, but they'll get it. So in Python, in GlowScript Python, box is an object. And if I give it a position and a size, then it will make that three-dimensional object. So I can assign it a name. I call it table. Box is reserved as the type of object. I give it a vector position, and this one I shifted it a little bit below the origin because I want to put things on the y equals 0 plane, just to make it easier to calculate. And then I give it a size. So this is a 1/2 meter by 1/2 meter, and then it's 1/2 centimeter thick. But you can change that. Okay, next, a hole. There's my hole. It's not really a hole. I tricked you. Okay, the hole is, and you don't even need that, but I want to put it there. The hole is actually a cylinder. So another object in Python, GlowScript VPython, is a cylinder. So for a cylinder, and I'll show you another one later, you have actually three properties really. The position is the location of one end of the cylinder. In this case, I put it down below the table a little bit so it'll stick through. And then the axis is a vector from the position from where it starts to the end location. So this is in the positive y direction. So it's a cylinder that points in the positive y direction. And then it has a radius, and I give it a color black so it looks like a hole. Get it? Okay. Now the mass. So here's mass 1. I need to I'm going to make this as a sphere, and it actually sticks through the table because I didn't really care that much. You could make it a disk on top of the table. That's not too hard to do, but I'm not a perfect artist. I'm just kind of an artist. I'm just trying to make it as simple as possible. So if you go back to the original Lagrangian, we can define the location of this in Cartesian coordinates. So it has an x value of r cosine theta. And this is important, right? Because I'm going to change the motion of the mass by changing r and by changing theta. So I need to get that back to x and y coordinates so I can actually draw the thing in Cartesian space. GlowScript uses Cartesian coordinates. So I can calculate r. I know r, I know theta, so I can calculate the x value of this ball. And in fact, this is wrong. This is not the y value. This should be the z value, right? Because the way I have this coordinated, it's in the xz plane. But again, z is just going to be r sine theta. So here's the coordinates for that. You can see I fixed my error. So a couple things. I need some constants here. C is the total length of the string, and I'm going to use that later. So then I pick a value for r. I'm going to just pick 20 centimeters because the table's half a meter. I picked a value for theta, and then M1 is an object. It's called a sphere. And so the sphere has really two important properties: the position, which is the location of the center of the sphere, and the radius. So the center of the sphere is a vector, and this just is r. And then you notice the x-coordinate is cosine theta. The z-coordinate is sine theta. And the y-coordinate is 0. Okay, so I fixed it. See? And then I pick a radius, I pick a color. The last part, make trail equals true. If you turn that on, if you put that in the object, then when the object moves, it leaves a trail behind. I think that kind of makes sense. Okay, here's mass 2. Nothing super crazy about that. I do want to, I need to know the distance below the hole, which I defined as the value s. So I need to first calculate s. And then once I do that, I can plot this object. It's just going to be, again, the position is negative s in the y direction, and then it has a radius and it has a color. And this one's a color green. Now what about the strings? So there is no string in, well, there is a curve, but there's no string in GlowScript. So instead, I'm going to make this as 2 cylinders. So here I have a cylinder on top of the table and then a cylinder below the table. And so these cylinders, again, have a position that starts at the hole. They start at the origin. And then the axis is the vector from that to the mass. So these are important things because I'm going to have to update these. But here is that axis. I drew that. I should have drawn it for the hole. But the hole was a super, super, super tiny cylinder, so it's kind of hard to see. So there's that. Now, what are we going to do? In the loop, when I draw this, okay, so I'm going to calculate my values using the numerical calculation I said before. And then I need to update the position of mass 1. I need to update the position of mass 2 based on r, theta, and s, which I can calculate. And then I need to update the strings too. And then that's it. That's what I'm going to do. Okay, so I'm going to jump over to Python and we're going to do this. I already have the table and the string and the masses built. I showed you how to do that. And then we'll just do the physics after that. Okay, so like I said, I've already started. I've already run this program too. Let me just show you that it does indeed work. So this is trinket.io. You can also use glowscript.org. There's also Python with the visual module, but I'm using this because I like to see the two things side by side. So here's the model I've already built, and it builds this 3-dimensional space that I can rotate around, and I can see how everything works. That's really nice about, not necessary, but nice about GlowScript VPython Trinket. So everything over here I've already covered, so there's no point in that. The next thing I need to do is start putting down my initial conditions. I already have the initial position of the mass 1 and mass 2. That's in that object. m1.pos is r. Okay, so I don't need to redo that. I do need the velocity, so I need r dot. So let's say r dot is 0.01. I'm just picking some values here. I don't even know anything. I need the angular velocity. I have angle already. I already have theta. Theta dot is going to be equal to, let's say, 8. I'm just, again, picking stuff. Now, I do need to calculate this constant L because I'm going to use that later on. So L, which I hate the lowercase l in Python because it looks like a 1, but this is going to be mm1 times r squared. In Python, squared is star star. Let's zoom this up a little bit. And then I have times theta dot. Oops. Times theta dot. And this was straight from that calculation before. Okay. What do I need to do next? I have theta, I have r dot, I have theta dot. Oh, I need time. So t equals 0. And then the time step. Let's put time step of 0.001. And we can change this and see what happens later. Okay, I think we're ready. So let's do while t is less than 5 seconds. I'm going to run it for 5 seconds. I don't like to use a really long time because if something goes terribly wrong, then I don't have to wait too long for it to fix. Here is the next statement, rate 1,000. So rate in Python, GlowScript Python, tells the computer how fast should you update everything. Since I have a time step of 0.001 second, or 1/1000th of a second, doing 1,000 calculations per second would be real time. Now, it might not be able to do it that fast, but this is what it wants to do. Let's zoom this up a bit. Okay, so now, just like in the presentation, I'm going to do exactly what I said. Step number 1 is to calculate r double dot. So r double dot, I'm going to use dd dot for r dot. It's going to be equal to mm1. Also notice here that I'm calling mm1 the mass, and compared to m1, which is an object. Okay, so you can't have those two the same thing. There's another way to do it, but I'm cool with this. So times r, I'm just copying down that equation that I had before. Theta dot squared, divided by m1 plus m2 minus, this is the second term, m2 times g divided by m1 plus m2. Now notice also g. G is 9.8. Okay, I'm using the scalar value of g because I'm not doing a vector calculation. I'm using my generalized coordinates, so that's important to note. Okay, so there's r double dot. Now from that, I can calculate r dot. So r dot is going to be equal to r dot plus r double dot times gt. It's that easy. Okay, and in this case, this is an expression to update the value of r dot. So I don't need r1 and r1 dot and r2 dot. I just do r dot. It just says take the value of r dot and make it this new value. Okay, so that's not an algebraic equal sign. Okay, now I need to update r. So r equals r plus r dot times dt. Again, straight from the calculation. Next, I'm going to calculate theta dot. So theta dot is from the Lagrangian. It's just going to be L, which I calculated above, times mm1 times r squared. Yeah, that's it. Okay, and then I'm going to update theta. Theta equals theta dot, theta plus theta dot times dt. And then I'm going to update t, which technically I should do that later, but that's fine. And then I'm also going to recalculate s. S equals c minus r. So that's my constraint. So c is the total length of the string, and I've calculated r. I want to calculate s just so I can use that value to plot the position of mass 2. So I've done the physics. Now I need to do the art. So the first thing I'm going to do is move mass 1. So I'm going to say m1.pos equals r times vector cosine theta. This is the same as before. 0 sine theta. Oh, not sint theta, sine theta. That's it. Okay, so notice that since theta changed and r changed, the mass is going to move. So that's it. Now I can update mass 2. m2.pos is going to be equal to the vector 0, negative s, 0. It's the same equation I had before too, but I've changed r, which changed s, so now the mass 2 is going to move. Now I need to move string 1. So string 1 is the one on top of the table. I don't need to move it. I just need to change the axis. String 1.axis is going to be equal to the vector from the m1 to the whole, from the whole to m1. So I'm going to say m1.pos, that is the position of vector m1, minus whole.pos, which is at 0, so it doesn't really matter. I think this is fine. I think the whole's not at 0. I'm gonna leave this like this. I don't think this is the best, but I'm gonna do it like this. String 2.axis is from the origin to mass 2, so it's gonna be m2.pos, and I think that's it. Let's save this sucker and run it, and let's see what happens. And be prepared for disaster, because who knows what's going to happen. Okay. Check that out. And you notice that it's moving kind of in a circle, but it's not in a centered circle around there. And so the actual the length of the string changes. It's not a constant speed circle. Let's run that again because I kind of like that. Let's rotate it around. Check that out. Okay, now I want to do what I said, and that is to make this in a circular orbit because we said that would be true. So up here, I can say, let's just comment this out and redo it. Theta dot, nah, you gotta spell it right. Theta dot equals square root mm2 times g divided by mm1 times r. If that should be the circular motion. Now I do need to change this up here too, because if I put it with an angular velocity that's circular, but r dot should be 0, right? So I need to put this at 0. And let's see if it moves in a circle. Check that out. Okay, and you really know it's a circle because this mass 2 doesn't move. And yes, you can see the mass from underneath because I made it that way because I'm silly. Okay, let's give this a little velocity. Let's say it's 0.3, and let's just see what happens there. Okay, so it goes back there. Now, you could do one more case. You could say, what if the angular velocity is 0, then it'll just fall down. Okay, I'll do it. Let's do that for fun. So let's say, just say 0 times this. It'll be dumb. Okay, so what happened here was that they don't know that the table ended, right? So it just runs forever, which is kind of silly. I could fix that, but I don't want to. So we're back over here. So this is not a circular orbit. Okay, now, is it legitimate? Is it totally legit, or is it totally bogus, or is it somewhere in between? Let's find out. Let's plot the total energy. Yes, I know this is a longer than normal video, but no one can stop me. So I'm going to make a graph. I'm going to call it tgraph equals graph, object graph. I'll link a video. I'll link to a blog post I wrote about how to make graphs so that you know everything you need to know. X title is going to be equal to energy. Y title is going to be time. So in this case, oh, and I gotta put units. If you don't put units, you get minus 5 points, right? Joules. And time is in seconds. What was I going to say? Oh, yeah, so in this case, there's no... energy should be conserved. There's no friction. There's nothing driving the motion. I don't have like a jiggle table or something like that, which actually would be really cool. What if the table oscillated up and down? Oh, wow. That'd be cool. But in those cases, energy wouldn't be conserved. But in this case, energy should be conserved. Okay. So I actually need to look at 3 energies. I'm going to say, I'm going to plot F1, FK1 equals G curve. Color equals blue. And I can put a label if I want. Label K1. That's the kinetic energy of object 1. And then I have FK2, G curve, color equals color dot green. Label equals K2. That's the kinetic energy of the two. Now I need the potential. So Fu equals G curve. Let's just leave it as black, but let's put the label as potential. Let's put it as just U. So in this case, we're really plotting the change in potential. So if I call the mass on the table doesn't really change in the Z direction, in the Y direction, so it doesn't have a change in potential. And then I'll say F total is going to be G curve. Which color? Let's use red. Color equals color dot red. Label. Let's just put it as E total. Okay. So now I have those 4 things. Now down here I'm going to need to calculate them, and this is a little bit more tricky, right? Because how do I calculate the values? So let's just go ahead and say, oh, I should really go back to the Lagrangian, which I deleted. Let's see. Here is, that's my presentation. I'll move that over here. Go back over here. Nope, that's it. Go back here. Okay. So here is my Lagrangian. I'm going back up here because I have T. Did I write it down? I didn't write it down. Okay, I did it in another thing. Let's see. Let me open. This is very unorthodox, just so you know. No. Open this file. Open recent. Model. Oh, I had it as a picture. Huh. Okay, let's see if I can do this from memory. T K1. Let's see. K1, that's kinetic energy 1, is going to be 0.5 times M1 times R1 R dot squared plus R times R times theta dot squared. R theta dot squared is, that's right. I'm pretty sure that's right. That's the kinetic energy for 1. Now for kinetic energy 2, that's pretty easy. It's just going to be 0.5 times m2 times r dot squared, right? Because the r dot is the velocity of the string, and this is just moving up and down. So this is just going to be times r dot squared. Wow, I think I got it. Okay, now the potential is pretty easy. That's just going to be mm2. It's going to be negative mm2 times g times s, right? Because it has a s is a positive number, but it has a negative potential energy. And then E total is just going to be K1 plus K2 plus U. Now let's plot all this stuff. So I have FK1 dot plot T K1. If this works, I'm just going to be so surprised. FK2, did I use capital K? No. Aha. Good thing. See? K. Okay, this is going to be an hour-long video, isn't it? Dot plot T K2 FU dot plot. And it's not FU, it's FU, right? Okay, it's the function U. TU. And then F, what did I call the other one? F total. F tot equals, no, dot plot T K1, I already calculated that, E total. Okay, let's see if this thing actually works. I just don't know. Okay, run it. Okay, the black curve, the red is E total. It's not constant. E total is K1 plus K2. Okay, so K1, K2. Oh, so yeah, I think this is weird because see here, K2 is constant. That doesn't look like it should be constant. Let me run that again. I mean, it is moving. That's weird. K1 and the red and the E total is changing. So I think I made a mistake up here. 0.5 r dot squared. U is changing. That's cool. See, this looks like K2 is K2. Did I label it wrong? E total is F total. Okay. K1 plus K2 plus K. So 0.5 r dot squared plus r times theta dot squared. I am pretty sure that's right. I don't have it with me. U and then r m2 r dot squared. Okay. I think I'm going to stop. I'm not sure. I'm going to have to figure this out, and then I'll post an update to this. But I just feel like my computer's going to explode because I'm recording too long. It looks good. I had to have made a mistake. I had to make a mistake with one of these kinetic energies. Kinetic K1 plus K2. See, I think it feels like if these two were switched, I'd be pretty happy, right? That looks pretty good. K1, I don't see a problem with. I feel like, okay. I don't want to be flustered and try to figure this out. I'll figure this out and either post it as a comment or post a picture or something like that. I will update you somehow. But I think it's working. I think. Well, let's just do one real quick thing. Let's make the time so smaller, and then that should make energy more conserved. If that works, I'm going to be upset. No, no, it looks the same. Okay, so that did not change anything. So clearly there's a calculation error on my part. I suspect it's something in here for the calculation error that makes the energy let me just double check. M1 r dot squared, that's kinetic energy, r theta dot squared. And this is just M2 r dot squared. 1/2 U K plus okay, I quit. Okay, I'll figure it out later. I'll talk to you guys later. Okay, I figured it out. It was a dumb mistake. You knew it was a dumb mistake. Let me see. Here's a snapshot of the calculation, and here's the kinetic energy right there. This part right here is the kinetic energy, right? So I have 1/2 m1 r dot squared, r squared theta dot squared. That was my mistake. Okay, So over here, I fixed it. So I put r squared, that's right over here. Let's see, r squared, theta dot squared. And then I reran it and check that. Look, it works now. I'm so excited. Okay, so here is the kinetic energy for mass 1. Here is the kinetic energy for mass 2. It doesn't move as much. Here is the change of potential energy. Add them all together, and ba-boom, constant winning. Oh, man, I feel so much better. I was kind of worried about the whole thing, but there you go. Okay.